Okay, so now let's start the main program. To I would say that tutorial of the main program. Okay, so yesterday we talked about some initial parameter settings and some preparation of the initial setting.
Yes.
Okay. Here. Okay, so first we read the curve data and the position data, and write the position data into PLC. And then
how you define the curve? Curve defined by the PLC or defined manually by you? The curve data.
The curve data looks the curve data is the relationship between displacement and deformation, right?
By experiment, right?
Yeah.
Okay.
Yeah. Initially, it is it has initial data from the simulation result.
Yes, from
Yeah.
from the simulation.
Okay, so
So which one did you use? You using by experiment or by simulation? By experiment, right?
Yeah. Now in the company's machine, it is simulation plus the experiment result. But now the experiment results data is much bigger than the initial data, because the experiments the numbers of experiments increases, and the importance of the initial data gets smaller. Right?
Yeah.
So here we read the curve data and the position data, and then we write the position data into PLC.
Okay.
And then we got a for loop for how much blade of a propeller.
Yes.
Okay, so for example, now we have 4 blades, so the K will go from 0 to 3. Right? 3, 1, 2, 0, 1, 2, 3. Yeah. It loops 4 times. Okay. So this is some communication with the machine, and here we have 2 overall test indicator. So the idea is that here is the first loop, right? So in the beginning we do a overall test here.
Yes.
So and then we'll check if the points need to be tuned, right?
Yeah.
So if the points get tuned, that means eventually it has to be overall test again, right?
Yes.
But if after we done the overall test, and it shows that in the discrimination it shows that it doesn't need to be tuned anymore, so you will go back to the beginning of the loop.
Yeah.
But how can we identify that it doesn't have to be overall test again? So now we use a indicator of the overall test. The overall test indicator is that we overall test indicator 1. So for example, we set it 0, and overall test indicator initially it looks like this, right? So in here, initially they are all 0. Yeah, and then after we finish an overall test, the overall test indicator will plus 1.
Yes.
That means that it's already done the overall test, right? So if it doesn't need to be tuned, when it comes back the loop, the overall test indicator will be 1, right?
Yeah.
But the overall test indicator 1 is still 0. Okay? So if they are different, that means it is already overall tested. So we can identify that this blade doesn't need to be overall test anymore.
Okay.
So in this discrimination, it says if overall test indicator 1 equals to overall indicator, that means it needs to be overall tested again. Okay. So if the two numbers are not equal, that means in the previous loop it hasn't been tuned. So we don't have to do overall test again. So this two indicator means that if they are equal, the blade need to be tested again.
Yeah.
If they are not equal, it doesn't need to be tested again. Can you understand what I'm saying? Yeah. So that's why after one overall test, this indicator will plus 1. And if it got tuned, the overall indicator 1 will become the same value. That means when it comes back to the beginning of the loop, it will fall into this discrimination, right?
Yes.
If they are not equal, it won't fall into this discrimination. That means that it doesn't have to be tuned again. It doesn't have to be tested again, right? So this is a small indicator that I designed for when does the blade has to jump out of the loop. If can you understand any questions?
For the overall test, it's mean test all the blade or
Yeah.
blade 1?
Blade 1, all of the point.
Oh, not all of the blade.
No.
Okay. Yes, I know. Okay.
So okay. So So this is for the loop of overall testing, and this indicator is for the whole process of this blade. That means now it's true, right?
Yeah.
So in this while loop, it will check if this finish indicator is true. If it is true, and it will keep working on this blade.
Yeah.
If this becomes false, it will move to next blade. Okay, so it is the whole process is covered by two loops. One is the process working on the blade tuning and overall testing, and a bigger loop is to check if we still need to working on this blade.
Yeah. Got it. So the small loop working on the point.
Yeah.
And the bigger loop working on the blade.
Yeah.
Am I correct?
Yeah.
Okay. Yes. Good.
Okay. Okay. So now, this is for overall testing, and here is some communications.
Between you and PLC.
A PC with PLC.
Oh,
okay. So here we print that the K+1 blade begins to do the overall test. Okay. So here it's communicating with the PLC that it tells the machine to do an overall test. And then it will recall a value that we can the program will know that here is we waiting for the response from the PLC to call back 21 the status code 21. That means the overall test is done. Okay, so we use this response trier function.
Response trier is a function.
Yeah.
Okay. Yes.
So here are few functions that this is for waiting for the response from PLC, and this is we write a value into the PLC register. Okay.
Write a value, it's mean write the movement. Movement of the.
Yeah.
Of the how to say range. Of the pin, no? Displacement.
This
displacement or?
For this part is it tells the PLC to do the overall test.
Or just to do the overall test.
Yes, it tells the PLC to do the overall test and where the starting and the end point is. Okay, so here you can see that the register I write in is the overall test start register to PLC, and this one is overall test ending register to PLC. So these two registers means the starting point and the end point of a motion on the blade.
Yes.
Right. So this variable, I name it pretty clear, is for overall test starting point and overall test ending point. Okay. And
really clear.
Yeah. And then after I told him the starting point and end point, I
what is the 1 and 2 or 2 1?
This is for as I just mentioned in the here and over here, you can see that in right mod bus here the last value means the space, and if it's pure integer, the space equals to 1. If it's float number, the space equals 2. So if you want to write a pure integer number into the PLC, you just write down the position of the register and the value you want to write in, and the space depends on the number you write in. For example, you want to write 3 into a register. It's a pure integer, right? So the space equals to 1. If you want to write 0.34, it's a float number, so the space equals to 2. So that's the meaning of the 1 and 2, right? So here we only input the pure integer.
Yes. So you write the registry by yourself?
What does that
I
mean?
mean, overall test, starting registry, did you write in Python or you write in PLC? This is the function, right?
Yeah.
This is the function from you or from the program?
From what does that mean? You mean that this function is written by me, or
I mean,
what is
this only this function
okay?
you write by yourself in?
You mean this one?
Yes, you define.
This is yeah, I define this variable.
Oh, so it's not function.
Yeah.
Okay.
That's a variable like this one. Yeah.
Yeah, you got it.
Yeah. So I name it clearly for the user to understand what's the variable mean. Okay.
Okay.
So, and then I tell him where to start and the end. Okay. So here I write the how to say that, the order the order of the order of telling the machine to start the overall test. Okay, so the machine start automatically, and then they finish the overall test process, and then it will recall a status code. So here, after the order, I will waiting for the response of the machine. Okay, and then this and then PC will stand by. So it knows I'm the PC is standby. PLC will also stand by. Okay. So now the registers in PLC records the deviation of distribution, right?
Yeah.
Sorry, the distribution of deviation, right? Okay, so now we use this function z measure refresher to update the measured value of the machine. So here, this one will update the deviation distribution recorded in PC.
Oh, yeah. Update.
Yeah. Okay.
Yeah.
So now the PC has the distribution. Okay. And store in a data frame variable. Right.
Data variable. Okay.
Yeah. Called position data. Okay. So here I print out the overall test is done.
Yeah. Oh, overall test is done.
Yeah.
Okay.
Okay.
Yes.
And then here overall test indicator +1. Okay. Okay. So now we enter a more smaller loop.
Yes.
Yeah. So there's 3 loops, not only 2 loops. 3 loops. So this is the smallest loop of the tuning. So in here we have to decide which tuning mode we are using, like I told you yesterday.
Yes.
Okay. So
Okay.
So here there are 3 discrimination of tuning mode, right? The first one is the total continuous tuning mode, and the second one is the continuous tuning mode.
Yes.
The third one is single point mode. Okay. Okay. So in a total continuous tuning mode is the reason that I told you yesterday is for all the points are much higher than a tolerance. We set for example we set 1.4 millimeter for the tolerance. The reason is that we need to make the whole distributions goes down, and for us to see the wave of the distribution, because the measurement has its limitation, that if the deviation is higher than a certain value, the program could not find the local maximum and local minimum.
Yeah.
Right.
Yes.
Okay, here. So here, if we decided to use a total continuous tuning, that means we need to tune from point 1 to point 18, right?
Yes.
But the structure of the propeller blade is different from where the point is, right?
Yeah.
For example, we got side A, side B, and side C here. Side A and side C their structure is much weaker than side B. Side B is much stronger. Side B's structure is much stronger than side A and B, A and C. So the displacement value we gave it to A, B, and C must be different. It should be different, right? So here we give the different displacement value to different kind of a structure. So here for this for loop, if This index A means the position of the points. For example, that if the point equals to 0, and that means point 1.
Yes, point 1.
And then we give it 4.5 millimeter of displacement. If here else if the point is under 0.15,
Yes.
under 0.15, we gave it the value of displacement 4.25. And here, if the point is over 0.15, we give it 300. Not 300. 3.0 millimeter of displacement. Okay, so here is a key point that if we want to write the displacement value into the PLC, you have to times the value of 1000.
Okay. 1000.
Okay, so for example, you see here, if we want to write 4.5 into the register, we should write 4500.
Yes.
Right? Okay, so in total continuous tuning, we give different structure, different displacement value. Okay, so now this is the order of this to tell the machine to start the overall continuous tuning, and then we wait for its response, and then we turn the overall test indicator 1 equals to the overall test indicator. That means when it comes back to the beginning of the loop, it will have to do the overall test again. This applies to rest of the tuning. It's a mechanism to make the blade, when it comes back to the beginning of the loop, it will make sure they will do the overall test again. Right? Okay. Okay, so that's the end of the continuous tuning, the total continuous tuning. And then when it comes to continuous tuning, the discrimination is if the number of the point, the deviation, if their deviation is higher than 0.4, and if the number is over 5 points, we use continuous tuning.
Yes.
Okay, so now these codes are for deciding the direction of the groups of the tuning interval.
Like
Okay.
yesterday you
Yeah.
told me.
Okay, so the first thing is that based on the result of total or based on the result of overall testing. Here we use this function continuous tuning to define the groups that need to be tuned. Okay? So this variable needs to be tuned are the groups that need to be tuned, like I told you yesterday. Okay? So here we decide the direction that the groups, for example, that if the middle point is 3, the starting point is 1, end point is 9, and then the direction is 1 to 3, 9 to 3. Yeah. Okay, so basically it's like that, and then we will give different displacement value to different number, different point. Okay, so now we still doesn't have to use the relationship of displacement and deformation.
Repeat. Can you repeat again? What?
For now,
Yes, for now.
we haven't used the relationship of the displacement and deformation, right?
Yes.
So the key point is that in continuous tuning and total continuous tuning, we doesn't need to calculate the value. We just gave it
A number.
Yeah, we just gave it a certain number. This number, yeah, for yeah.
So the relationship between deformation and deviation is just only for single point?
Yeah. Yeah. Okay. Okay, so we just give it a certain value to each point. So after that, we waiting for the response from the machine that the continuous tuning is done, and then we will make the overall test indicator 1 equals to overall indicator to make sure it will do the overall test again. Okay, so here's the process of the continuous tuning, and then it comes to single point tuning.
Yes.
Single point tuning is that the first thing is here is we find the largest deviation of the distribution. That means we find a point that it has a larger, has the maximum distribution, the maximum deviation, right? And then here this discrimination is to check is every point is under the tolerance. That means let me ask you a question. How do we know everyone is under the tolerance?
How do we know?
Yeah. How do we know everyone is under the tolerance? So
using if function.
The method here is if the maximum value is under 0.2, then everyone here must be under 0.2,
yes,
right?
Yes, correct.
So okay, so the discrimination here is like that. If the largest deviation is under 0.2, then everyone must be under 0.2. Okay, so
and we do the single point tuning.
And in this case we don't in this case we will break the loop. If there's a point, if the highest point is over 0.2, and then we should tune it, right?
Tuning, yes.
Yeah. So so here is the discrimination that if there's any point over 0.2. So here is the else is that there's no point under 0.2. Okay, so
we can conclude that the tolerance of deviation is 0.2.
now it's like that, yeah. We set it 0.2, but this is a variable, so we can change it.
Okay. Yes.
Maybe 0.3 is okay. Yeah.
Yes. Okay.
But as the tolerance go smaller, it will be much harder to tune it, tune every point under the tolerance. Yeah. So now we set it 0.2. Okay. Okay, so now we found out that there's still points need to be tuned, right? So here, write Modbus the position register to PLC. We write the maximum point.
Yes, maximum point.
So here is Pmax plus 1. That's because that in the data frame, its indicator will
get the plus 1.
Yeah.
Start from 0.
Yeah. So here we plus 1. Okay, so here we tell the machine to tune that point, and then we waiting because there in single point tuning there will be the process will be measured, tuned, measured.
Yes.
Yeah. So after we tell the machine to tune a single point, it will go measure that point first.
Okay.
So here we need to update the measure value of the deviation first. Sorry, we need to waiting for the machine to tell us that the first stage of the process is done. The first stage is measured, right?
Okay.
So and then if it's done, we update the measured value of the deviation. Okay. So here now we know if I said update is to update all the value in the deviation, because my function you will check the z measured. This is in PLC. PC. Okay, so if I use the z measure refreshes this function, the program will read each register on the z measure register, and then copy back to the deviation data frame. Okay, so for example, that now is the maximum number is 3, and we copy all the columns back to our position data, and then we check point 3. Maybe the deviation is positive 0.35, for example. If the situation is like this, what's the direction of the displacement?
Should be go down.
Yeah, should be going down, right? So the displacement must be negative.
Yes, must be negative.
Okay, so here is the discrimination of the direction of the displacement. Here, if the deviation of that point is greater than 0,
yeah,
the direction is negative.
negative.
Oh, I said positivity. it's a negative, but else that means it's the deviation is smaller than 0.
It should be positive.
Positive. So the positivity, we don't need to add any prefix here. Understand?
Yes.
Okay. So here I print out the deviation is greater than 0. The displacement direction is negative.
Yeah.
Here the deviation is smaller than 0. The displacement is positive. Here, okay. So here we decide the direction of the displacement.
Yeah.
And then we need to use the curve to calculate the displacement.
Yeah.
Right? So the first thing we need to do is to define which side the point is. In which side the point is.
Which sides?
Yeah. For example, in point 3, it's in side B, right?
Yeah, yeah.
Okay. In side A, side C.
Okay.
In this one.
Oh.
So
yeah,
now
yeah.
we have to decide these. What's the point? Now we are considering where in which the side the point is in. For example, yeah. For example, 3.3 is in B. 16 is in C. Yeah, yeah. Okay, so this discrimination is to decide which their side is. So here, if P max equals 0, that means the point is 1, right?
Yep.
So it's in side A.
Side A.
So if the P max is under 13, that means it's below, point
B.
Yeah, it's in side B, right? And then else the rest of it is inside C.
So if the point is 2, is inside C, because
Yeah.
the point is 2, is that is inside C.
Yeah.
Why not inside A?
It's quite complicated, but
Because
in this graph, this point 2 is inside A, right?
yes,
But
in your program, point 2 is inside C.
This is only for the demonstration. To let you understand the concept. But in reality, after the experiment, that now we think that this is a much better combination of the point. That this is before the experiment, that we assume that it can be defined as 3 sites. And after the experiment, that we think that only point 1 can be site A, and yeah, it's like that. Okay. So a lot of parameters in this program is from experiment and experience. Actually, a lot of things is out of our assumption. After some experiments, we found out that some condition is different from our assumption. So we need to adjust the parameter to fit the real situation of the propeller tuning. Okay, so the concept is the same.
Yes.
But the details are different from the assumption. Okay. So now we can find the point and its site. Right. So, and then we need to take out the relationship equation, right? So here in the curve data CSV file, it looks like this. It looks like this. The columns looks like this in a curve data. So here we got the site A1 value and site A2 value. This 2 value means the x and y. Means the x of site A and the y of site A in the curve data file.
Okay.
So this is the x for site B and the x for site C, y for site C.
Yes.
Okay, so now so you can see here we use a data set. We take out the site, for example A1 values as the x value. Okay, so we take out the site A1 value as the x value, and then site A2 value as the y value. Okay, so now we have these 2 values, and then we can use the polyfit.
Okay.
To do a 2-degree polynomial regression. Right?
Yes.
So you can see that P is the equation parameters. So we use this x and y to came out with the equation that you already know how to do that. Then we use the solver to solve the displacement value, right?
Yes.
As TR1. Okay, so now TR1 is the ideal value of the displacement, right?
Yes.
Ideal value of the displacement using the curve we came out, right? TR1.
Okay. Yeah.
Okay, so this is original value, and then during tuning we will face a lot of problems. We cannot just using this value. So I will explain. Okay, so first is that during the tuning we will face two challenges. First one is the string hardening.
Yes, string hardening.
The second one is the Bolsinger's effect.
Yes, Bolsinger effect.
Okay, so okay, so if the string hardening occurs, that means the elastic region will increase, right? So the curve must be shifted like this, right?
Yes.
But when the Bolsinger's effect occurs, the elastic region will become smaller. So the curve must be shifted like this.
Okay.
So we need to adjust our original displacement value to fit the situation that when the string hardening occurred and the Bolsinger's effect occurred. So here, but how do we know if the string hardening occurred and the Bolsinger's effect occurred? We don't know, right?
Yes.
So by experience.
Experience and experiment.
Yeah. By experience and experiment.
Yeah.
The string hardening must occur once the numbers of tuning increases.
The number of tuning. Oh yes, I know.
Yeah. So that means if you tune a point too many times, the string hardening must occur. So so we can set a threshold of numbers of tuning to decide how much we need to shift the curve.
Yeah.
Right?
Yes.
And the same as the Bolsinger's effect occurred, if the Bolsinger's effect occurs when the previous tuning direction is different from this time.
Oh.
Right?
Yes, opposite direction.
Yeah, the opposite direction gets weaker. So here if the numbers of tuning is smaller than 3 times, we can assume that it doesn't have strain hardening. Okay, there's 3 thresholds: 0 times, 3 times, and 6 times.
Okay.
So if the numbers is not bigger than 3, we can assume that the strain hardening doesn't occur.
Yeah.
We can use the original value of the sulfur comes out. Okay. But if the number is over 3 times and lower than 6 times, we can assume that it is slightly affected by the strain hardening.
Yes.
Okay, so the TR1 value comes out, we need to add a certain number. Add a certain number of the tuning. For example, we add 4. Here's a quite tricky part is that we
How to do that?
Yeah, we need to adjust that into a useful number. For now, we times the original number into 0.1 and plus 4. That means that it's quite hard to explain this. It's because that I think you can just you can see it as some kind of adjustment of the algorithm, but the concept is like that.
Yes.
It is why I just told you that if the number is between 0 and 3, the displacement doesn't have to. We don't have to adjust the number.
Yes.
So if the number of tuning is over 3 but smaller than 6, we need to slightly adjust the number. But if it's higher than 6, we have to adjust the number harder.
Yes.
Yeah. So okay, so this one we solve the strain hardening problem, and then the Bosch's effect is that when the direction is opposite, we need to make the displacement value smaller.
Okay. Yes.
Okay. So here here is the adjustment for the displacement value is positive, and here is positive. This one are for Bollinger's effect. Okay. This here is quite complicated because we change the algorithm here many times because we change the algorithms many times by the experiment. So this one is I don't know how to say it, but it's quite tricky because the design of the mechanism changes a lot during the development. So the variables changes a lot. For example, that if now we use the first design and we tune it and the model of the relationship becomes perfect in this moment, and next week they change the design of the force lever and the contact pin. The whole variable changes a lot. The model you just trained last week doesn't work this week. So you need to keep go to a company and do the experiments and then your models can keep up with their current design. Yeah, so yeah, it's just like that. And then what's this?
But before you leave, the first model of Sidu's propeller is already finished, right?
I think it can be. I think it's 80 to 90% of propeller can be calibrated, can be tuned. But
and what is the rest?
Rest is that their deviation is quite strange. Yeah, so something like, for example, much lower deviation or something like that, because that for example, this is the blade edge. The mechanism needs to go into the blade, right? Okay, the control scheme they use right now is they follow the ideal position of the CAD model. So for example, the ideal position of CAD model is like this, but the untuned propeller maybe look like this. There will be some difference, right? If the difference is not much, it's okay because the mechanism won't hit the blade, right? But if the propeller looks like this, it will, if we still follow the ideal position of the propeller, it will hit blade. So that's why some of the propeller cannot be tuned is because their control scheme right now cannot handle this kind of situation. So the propeller that we do the tuning cannot be too, how to say that, the deviation cannot be too much or too small, too low. Yeah. So maybe 10% of propeller will have this problem. Yeah. So that's another story. But okay, so we come back to this part.
Yeah.
So if the original value of displacement is tr1,
Yeah.
And then after our adjustment, we define the value that after adjustment is tr2. So tr2 is the final value that we gave it to machine. So
which one?
tr2.
Oh,
Yeah.
yes.
So tr2 is after our adjustment. Okay. So here, previously we just defined the positivity, right?
Yes.
So here we write the Modbus, write the register, tell the machine that later the direction is positive or negative, right?
Oh, yes.
Yeah. And then we write the number first. Right. Sorry. Hold on. Here. We write the displacement value and the positivity at the same time.
Yes.
Sorry.
Oh, at the same time.
Yeah.
Okay.
So for example, it's negative, like this, or like this. Yeah. So we write the register with the positivity and the displacement value at the same time. And then we waiting for the machine, because the machine goes to tune the plate, and then we waiting for the machine to tell us that the displacement has done, and then we need to update the measure value, because it will be tuned, measured, right? So here now we are here. It measured again. It measured that point again. After the displacement, it measured the point 3 again.
Yes.
And then we need to update the deviation measured again, right? So here we use z measure remeasure again, and then we need to calculate the real value of the displacement, of the deformation. Okay, so the idea is that we have the original value of the deviation, right? For example, 0.45.
Yes.
And then after our tuning, the deviation becomes 0 to 6, for example. Okay, so we need to calculate this value is 0 1 time, right? So this is the real deformation value. And then we have TR2, right? TR2 is the real value that we give it to the real displacement value. TR1, sorry. TR1 is our calculate value. Okay. So now we have TR1 and the real this deformation value, and then we can use this relationship recall back to our database. So this two can update our curve database. Okay, so after times of single point tuning, there will be new data points comes into our database, right?
Yes.
So this part is for that. It is that we optimize our mathematical model of the curve data. Okay, so now we calculate the real deformation real. Yeah. Here we calculate our real deformation, and then we enter here. You can see this function data frame writer is that the curve data frame, and then its site, and then TR1 and the real deformation value back into our curve data, right back into our curve data, and then we turn the whole database into CSV file. Okay, so after this tuning, the CSV file will be updated. The curve CSV file will be updated, right?
Yeah.
Okay, so here we got a counter +1. That means that we will recording the total time that we will do the tuning at the same time. But I think this is not important. But I think this is not that important. It's you can delete it anyway. And okay, so this one is after our tuning, we still need to make the overall test indicator 1 equals to overall indicator. Okay, so here is to show that if the deviation of the point is under 0.2, this discrimination is not important either. It's for us to see if this point is under 0.2 now. It just shows us the result, but it doesn't have anything to do with the whole process. It's just to show us the point we tuning now if it's under 0.2. So this part is not important to the whole process, but can show us if this point goes under 0.2. So okay, so after that, after all these codes, it will goes back to the beginning of the loop here. Sorry, here. Okay, that is true. go back to here, and then we assume that every point is under 0.2. It was do the overall test again. Then if every point indeed is under 0.2, this finish indicator will become false, and then we escape this loop. And here we said in this propeller, for example, the first place tuning complete, and then we goes to next blade. Okay.
The program will go back.
And the program will go back to the beginning of this for loop, the outest loop. Yeah. Okay. And then do the same thing again until every blade has been tuned. Okay. Until every blade has been tuned, it will escape the for loop and then come to the last line of the program.
Escape the for loop.
Yeah.
It's like I'm trapped inside the for loop.
Yeah. After the 4 times, finally we can escape the for loop. And then here, all the blades of this propeller is completed. And then it tuned for how many times?
Oh, many times.
Yeah. So this counter is this one. Okay. So that's all for this program.
Really?
Yeah.
Wait. Oh, but the define.
Yeah.
Is
Yeah.
important.
I think I explained in the Word file.
Oh, yeah.
Yeah.
Okay. And also I have your video in the.
Yeah. So that's all.
Okay, got it. Wow, only 1 hour? How much time? 1 hour.
Yeah. 1 hour and 20 minutes. Okay. But there's still a lot of details that you need to understand. Otherwise, you don't know how to change my code, right? Because that in the future, you must need to change my code, have the ability to change my code. So the first thing is that you need to understand all the things of this program. Okay. So there's some important things that I want you to know is that in single point tuning, you can see that here the code is quite complicated, right? That's because this result is by the experiment. So if we change the propeller model, this one might not work to another type of propeller. So that's why you need to do the experiment to build their own model of the other type of propeller by experiment. Because for now we still doesn't have a clear procedure to make sure what the model is. Because during my during my research that the software and the hardware are developing at the same time. So they change their design a lot, but the update of the software is not fast enough to keep up with their change of design. So the only thing I can do is go through Sense and keep doing the experiments and try as hard as I can to come out with a mathematical model that can fit the situation of the current design. So this part that for other type of propellers that you need to do it yourself with the engineer in Sense.
Engineer in sense,
Yeah.
is they can read your coding.
Yeah, so that's why I add a lot of comment on my code. Yeah.
But they can read your coding, right?
Yeah, I think that because we work very closely, so he must know most of the procedure during the tuning process.
Because
Yeah.
if some if I
Line.
made a mistakes on my coding, so they can check something like that. So we cannot we not cause the trouble for the machines, like broken the pin or something if I wrong to input the value.
I think that part that you don't need to worry about that because that's the problem of the control and electric engineer for that machine. In this program, you only need to tell the machine to do what kind of motion and which point and the value you gave it.
Yeah.
Yeah.
But
But
if I do wrong, input the value.
so that's why we need to set a maximum displacement value and the minimum displacement value here.
Oh.
So at most, we limited our displacement value, so it won't goes wrong during the tuning. And the rest of the problem is the electric engineer. Yeah.
Okay.
So I think it's not that dangerous to make the machine crash. But for the control and electric engineer, that happens a lot.
It's really dangerous for the.
Yeah. So we don't need to worry about that, and we just only need to figure out the idea of the algorithm. Because this is not perfect enough, there's still some problem. As you can see that last time go to the first time we go to Sense, I want to demonstrate you the whole process. Yes. And the machine crash, right?
Yes.
That's because the control scheme hasn't been done yet since the change of the design. So that's why the machine crashed. It's because they just changed the design of the mechanism. They haven't come out with a suitable control scheme of that mechanism. So in here we only need to worry about our tuning algorithm. Okay. Okay, so the only two things will cause a problem, make the machine to crash is, first thing is the maximum displacement value. You if we set the maximum value is 7, the displacement won't get higher than 7 and you won't be any dangerous during the tuning process. But the second thing that might cause the machine to crash is the position data you enter here. Yeah, if you give the machine wrong position data, your maybe it goes like this, right? Because the position is wrong from the beginning. So but that won't happen. I think that won't happen because the code is here. Yeah, it is here, and I think it won't cause trouble during writing the value into PLC. The problem will happen when you're generating those points. If you generating the points using a wrong procedure, then it comes out with the wrong result of the position data, and that causes the trouble. Not the procedure writing the value into the PLC. It's when generating those points. So you need to be careful on on these two things, and I think the rest of it is okay, because they always have how to say that? They always have a spare part of the machine. Okay. Okay, so I think I can stop recording here.